So this talk is on a slightly different angle. So what we're trying to do at Swansea University so far is address the transmission problem by trying to see how we can really remediate the problem of deposition. And we've had a fantastic team here to start with, who was made of mostly chemical and materials engineers, and it came up with a great idea of trying to sterilize indoor spaces. It started with ambulances using ozone. So ozone is fantastic, a great oxidizer, is doing a great job, provided we can reach sufficient concentration to effectively kill the virus, but it doesn't just affect viruses. It can be a little bit more generic than this. So this was quite a big team. It was a very big team, in fact, and they called on us as a team of modelers to look at a little problem that they had. Effectively, if they want to check that every nook and cranny of the rooms, the ambulances, has been effectively disinfected, they're going to need a near infinite array of sensors. This is just not feasible. So they asked the CFD experts in the College of Engineering here at Swansea whether we could model it rather than have to measure it. So this is what we did. So we set about effectively having a collaborative project with the experimental and computational aspects side by side. Today's work is effectively the computational aspect of it. There's going to be a little bit of input from the experimental side for validation, of course. The work for the validation process has been accepted for publication already, and it was written up by my colleague Hamid Tamadon-Jeromi. It should be available very soon in the International Journal for Numerical Methods in Heat and Fluid Flow. And the aim of the computational thread of the project is to validate the numerical modeling approach. So how did we go about it? Well, we didn't really reinvent the wheel. We went with a very classic formulation. We went with the finite volume method using the Navier-Stokes formulation. We've got here an incompressible formulation, quite simply. The transport equations were modified a little bit to add a buoyancy source terms here, effectively to account for the fact that we may introduce a secondary species of different density into the transport. I'll present that in the next couple of slides. And then we needed to take into account the turbulence in the room. We used a very simple model, the Spallart-Talmaris one equation turbulence model. We've got one equation, one transport equation solved over the whole field, and the rest is sorted with local equations of state. So it keeps the overall system of equations fairly simple. To solve the scalar transport model, we chose to model simply the concentration. That's the concentration of ozone that we're injecting into the room, or the space that we're looking at. And it's a standard convection diffusion problem here. But what we've added here is a couple of terms. We've got a source term, which is going to be based on flux, where we inject the ozone into the room. And here we've got a destruction term, which is a pseudo first order destruction term defined by this coefficient K. And then that gives us something that destroys ozone proportionally to the concentration present. So this is effectively our equation for the transport model. We couple that with the overall momentum conservation equation, and this is the buoyancy source term which you can see is dependent on the concentration and obviously gravity. And you can see this Y here is our vertical direction, chosen direction. So it's fairly simple. In terms of source term, we've got a flux source term in the locations where we inject the ozone into the room. So the flux simply ends up prescribing what is an inlet velocity for this scalar. And as I said before, this is our sink term here defined by the coefficient K. So that's pretty much the setup that we used. What did the model actually look like? Well, what we had was a fairly standard commercial unit. It's an ozone generator. It's got an inlet which has a fan through it, so we modeled that. We've got two separate outlets. One of them is in generation mode and it goes straight up, and in destruction mode we've got a flow straight through the unit. The flow rate is dependent on the working mode of the unit. And the flow rate is implemented as a simple pressure rise through the unit. You can see that it's different simply because of how convoluted the path is within the unit. We need a much greater pressure rise from the fan to actually get it through to the ozone generation outlet than we do for the ozone destruction outlet here. The validation case was kept very simple. We got a simple cuboid classroom. We've got a great facility here at Swansea University, which was originally built to try out, I'd say, the energy aspects of the building. So the ventilation is very modular and it's got great control. And we thought, well, this is a great facility, but we could also think of another use for it. Having good control on the ventilation of the room made it the ideal place to try out our little sterilization problem. So we put the ozone unit in there. We removed the furniture for the first trial validation case. We had 4 sensors that we disseminated throughout the room, and we tried to put them in interesting locations, so right in the corners of the room, roughly in the middle of a wall, and then up near the top, it was attached to one of the light fixtures. The way this works, we've got an ozone production regime followed by the ventilation time. So ozone is neither destroyed nor generated during that period, followed by an ozone destruction time. We've tried a number of cycles. The first one with 3 minutes of generation followed by 2 minutes of circulation. The second one, we had 4 minutes of generation and 1 minute of circulation. And the third one, we've got a full 5 minutes of generation time, no circulation time. Either way, we ended up having 10 minutes of destruction time afterwards, which was just to make sure, or at least 10 minutes of measured destruction time, just to make sure that the room was safe with sufficiently low levels of ozone in there for people to re-enter. We've got a little animation here of the results we got. If I can get to it. There we go. So you can see that there is a very clear plume coming straight out of the generator. And very, very soon, we've got levels well above 4 milligrams per cubic meter. Once the generation time is finished, it's very, very soon a homogeneous distribution throughout the room. So the ventilation is very, very effective at distributing ozone throughout the room. This was my backup slide in case animations didn't work, but the interesting parts here really show that we've got a nicely averaged distribution of ozone here throughout the room very soon at 300 seconds, 5 minutes. And this is for the case when we have 3 minutes of generation followed by 2 minutes of ventilation. How did that compare to the experiments? This is where we had a little bit of a surprise. So what you'll note is that the case that we used for the experiments had 3 minutes of generation and 2 minutes of ventilation. The reason why we modeled different cases numerically was because the output from the experiment raised a few questions. It turned out that using a commercial unit isn't quite as simple as flicking a switch on or off. So once the unit is switched off, we still observe a very significant output of ozone from the unit. That was quite interesting, which raises more questions about the real-world relevance of the ideal assumptions made when we carry out a modeling exercise. The model behaves really well in the parts where we've got the rising front of degeneration. We can see that we can reproduce that really accurately, and it follows through regardless of location, right in the corners of the room. So this was really interesting and probably one of the main outputs from this particular project. That means that we can actually define whether we reach into possibly one of the more hidden corners, the places where we thought the flow wouldn't go. So what we decided to do next is to take that to a slightly more complex room. And it looks simple. The one complexity we were looking to introduce here is the fact that we've got a wall unit here and some worktops. So what happens in between those? Can we actually, with a single unit in the middle of the room, reach everywhere, or do we have to introduce some very complicated systems to sanitize our rooms? So we used the very same model, and here we've got a slice throughout the model. So we can observe the concentration rising. We've got this very characteristic plume, quite simply characteristic of a very powerful fan. More interestingly, we've got this sweep, and we're going to look at this area of interest here. So at the end of the simulation, time for injection of ozone, so at 300 seconds, we can see that we've got an ozone concentration index that's really high. So basically what this means is that we've reached a level of concentration which is very close to what we inject from the unit. So when we sweep through here, there we go. What we're looking for is any indication that this index is dropping significantly. And one of the really good outcomes that we could see here was that, well, it doesn't. Why was that? Well, quite frankly, this is because we've got a unit in here which is possibly not necessarily looking too much at energy efficiency. We've got a really, really high ventilation rate. So that was possibly a bit of an overkill. But in the grand scheme of things, does that really matter? We're looking here to make the indoor spaces secure. So no, it doesn't. The take-home message we got from this is that it doesn't necessarily require a very complex circulation system. We've got here a room which is fairly large, with a 55 cubic meter to be specific, with a single unit in the middle of it, which can be sterilized in a time well under 10 minutes. So in the conclusions, really, what we wanted to highlight is how the method really described accurately the diffusion of ozone as a solute phase throughout the rooms that we had. It really matched well in the circulation phase and the generation phase. We didn't need to use a very advanced model. We had a very simple turbulence model. We had to couple really the overall flow throughout the room with the alterations due to the difference in density. So we added a buoyancy term in there. We've got some very simple boundary conditions to get the flux and the distraction terms. Beside that, well, for full disclosure, the model was implemented in ANSYS, ANSYS Fluent. So commercial software is up to the task if you can code the user-defined function into it, really. The numerical results are in good agreement, and the only thing that I would highlight here maybe is that it does take significant computational resources. So to get a satisfactory result, we had to use 1.14 million cell in the validation room, which is a very significant number. That took us to roughly 3 days worth of computing on a 28 core machine. So the computational load here is maybe a little bit more than you would want to do practically at I'd say a day-to-day level if you were to assess the effectiveness of disinfection on a room-by-room type of basis. So where are we taking this? Well, this last point I made is really maybe the drive for the future project. We're looking to simplify that a little bit, make it a little bit more accessible. So we're taking it to in-house code, see how we can make that a little bit more efficient, how we can scale this to buildings rather than just single rooms. There have been a number of cases reported where transmission was going above partition walls or through the ventilation systems between rooms. What we'd like to achieve here is really a piece of software that would enable us to, first of all, combine with all the transmission models that a lot of authors are presenting much better than I do, or than I would this morning. Combine this with the remedial solutions that we can come up with. And what we're looking for here is a microbe secure indoor space framework. So either to assess how existing spaces are safe or can be made safe, and maybe optimize this as well. I think that's taken me pretty close to my 20 minutes. So I'll leave it here for now. Thank you very much.
Thank you very much, Sam, for a